Hello, Internet, and thank you very much for tuning into the Cloud Native FM podcast YouTube channel. I hope you are listening to me correctly. If any issues while hearing me, feel free to comment to the section so I can notice you can hear me correctly. But thank you very much for tuning into this show. Let me share what we're actually covering today on this today's podcast. In the recent years, both WebAssembly and containerization have gained significant traction in the software development landscape. WebAssembly, often abbreviated as WASM, is a binary instruction format that enables running code at near native speed in web browsers. On the other hand, containers have revolutionized the way applications are deployed and managed, provided a consistent and isolated environment for running software. Join us in welcoming Matt on today's show. He is a co founder of the most used CNCF project named Helm, and now he's the CEO of Fermion Technologies. And is this Fermion is at the forefront of the WebAssembly wave. We will be exploring together the powerful synergy between the WASM and container, understand why they complement each other so well. The start of the third wave of cloud computing, isn't it? And also the state of the WASM ecosystem and the what Freemium doing in this space. So without any further delay, thank you very much, Matt, on being on the show. Let us know where are you busy currently at this moment of time, and then we'll start the agenda.
Yep. Thanks for having me. It's exciting to be here. Fermion Technologies, we started just around a year and a half, 2 years ago. And we've really, the kind of main idea we wanted to pursue was, is it possible to build kind of a third wave of cloud computing? If virtual machines were the first, containers the second, is there a third wave of cloud computing coming? And what would be the core technology behind that? And for us, as we looked around and tried all these different technologies, WebAssembly very quickly sort of bubbled up to the top. And we said, this is it. This is the thing that is going to complement these existing technologies, introduce some new features, and solve some problems that we've been trying to figure out how to solve for years and years now.
Awesome. Absolutely. And I think like right now we see a lot of traction if in the ecosystem, in the Kubernetes fittings and the cloud native. If you look at the waves, currently there's a two very hot waves coming up. One is platform engineering, and the next awesome wave is WASM. And WASM has a lot of the conference being held up, and Matt will give us insight. Like I think he will be on the WASM day, and now in the KubeCon Chicago, the WASMCon is happening. So without starting some question around WASM and container, what are your experience of these dedicated conference to the WASM, just the one technology? Can you share some experience for us?
Yeah. Okay, so the other day, my daughter found a video of me speaking at the very first KubeCon. And my hair was a lot browner and actually a lot longer back then too. And I realized, that moment, I'm like, I'm living that again in another environment now. So the, first WASM day was a couple of years ago. That was a pre-day for KubeCon. WASM was an event that happened in Barcelona earlier this year from the same people who put on Spring I/O, the Java conference. And now WASMCon is coming in September in Seattle, Washington, I believe is the location for it. And the energy around WebAssembly right now, it just reminds me so much of what it was like in the early cloud native ecosystem. It's just, people have the technology is still new enough and enough core work is left to do that people come in and they can make these gigantic contributions with only, a few hundred lines of code. So it's still kind of that environment that's just vibrates with the potential to build new and interesting software right at the beginning of this ecosystem. So I'm really looking forward to WASMCon in September, looking forward to WASM Day in Chicago in October and November. And both I think WASMCon is going to be a little more approachable for people who are outside the cloud native ecosystem. So if you're getting started with WebAssembly and you want to kind of figure out how this works in IoT and Edge and all these other environments in addition to cloud native, that's a great place to start. And then WASM Day will continue its sort of focus on cloud native and how cloud native and WebAssembly really work together, which of course is where Fermion, where we think we are in that ecosystem.
Yes, absolutely. I think the WASM, if you look at the one technology is gaining traction and has a one full flash dedicated conference dedicated to it. Look at the scenario what people are talking about. They're talking about hybrid and edge computing. They're talking
Hmm.
about the containers has a very problem or very long running problem of having giant containers, so many
Hmm.
packages backup libraries had so many code inside it. How do we secure it? We see like there's a wave around shorter and skinnier images for your containers,
Yep.
but the WASM can actually, this off the load from us. That is all the WASM con and the WASM day. The playlist available on the YouTube. Go watch it. And what a wonderful talk available on the Fermion technologies for the Matt around WASM. I think he's a keynote on Open Source Summit. The link is also available on the chat. So let me start the first basic question. So how does WebAssembly is fit into the containerized ecosystem?
Yeah, the way that we have thought about this over time is like, and we'll go a little bit before the container ecosystem and talk just for a moment about virtual machines, right? Virtual machines are really the core technology that created cloud, right? We would not have cloud if virtual machines had not come around, but they were really big and really hefty, right? We were talking gigs and gigs in size, and they were designed to run from the kernel and its drivers all the way up to the top level application stack, an entire operating system bundled up together. And containers came along, and they offered a more focused approach to packaging up and distributing and then running individual servers. Where instead of packaging the entire operating system, we're just getting like a little wedge of an operating system. It's just the application you want to run, the libraries that application needs, the chunk of the file system that application needs, and maybe some utilities and things like that. So we start with like a very pared down, version of Ubuntu, or a very pared down version of Debian or Alpine or any of those. And then we just add back the bits that our application needs. But both virtual machines and containers were really oriented around long running processes, right? Servers, essentially, where you start up a server, you listen on a port, you set up your TLS configuration and all of that. When you're being charged to run by the minute, when a cloud provider charges you by the minute, then you start saying, maybe there's a way to do shorter processes that would do a smaller chunk of work. And the main paradigm that kind of evolved out of that was serverless functions, right? AWS Lambda was an example, Azure Functions, Google Cloud Functions. Those are all examples of this model where, as a developer, the chunk of code you're writing is just an event comes in, I handle that event, and then I return a response. So it's a very small and concise chunk of code that's just designed to run, to do one thing and do it as fast as possible. So it starts up, runs, sends back the response, shuts down. Event comes in, starts up, runs, shuts down, And so they live, instead of for hours, days, months, whatever, they live for milliseconds, seconds, maybe minutes at the top end. And so we're looking at that technology and going, we really need sort of an actual cloud layer that can really run that kind of workload very well and can be portable, and you're not locked into one particular vendor, you're not locked into one particular platform, you can kind of move these workloads around. And that was kind of the root that got us interested in WebAssembly. We're looking at that kind of workload and saying containers are not going to be a great runtime for that. Virtual machines are not going to be a great runtime for that, particularly not if we want millisecond startup times. But WebAssembly was looking very promising. And so we really began investigating how to build a serverless functions platform based on WebAssembly. And now the interesting thing about this, and then I'll pass it back over to you, but the interesting thing about this is it's not a replacement for containers or a replacement for virtual machines, right? We found this problem that needs to be handled and needs to be done really well, but it's not going to replace all the kinds of stuff we've written with the others. Well, that raises a whole bunch of additional challenges, which we'll probably talk about throughout the day today, about how to work together, how a container and a WebAssembly module should work together. What kinds of applications do we build? Why would we build them this way or that way? And that, to me, is one of the most exciting things as WebAssembly really starts to take off, is seeing how it solves some problems and then begins to sort of fit in with these other existing technologies, like containers.
Yes, absolutely, absolutely. I think if developers are listening to us, I think kind of interesting to for them is like during the virtualization era, there is so much of the work developer has to be done. They need to spin up the virtual machine. They have to
Mhm.
install a Linux operating system, then the Linux binaries, and then they install application on top of it, and then they write the code. And then there is another developer within the team. He's using another virtual machine that has another Windows. Might be they're using Windows operating system, and that the Windows
Mhm.
specific binaries and the Windows specific app requirement is now, and then installing the app on top of it. There's a huge cognitive load for between,
Yeah.
and now we actually
Yeah.
end up. It's work on my machine. Don't mess with me. It's your fault. Go and get that the environment I am in. And then their
Yeah.
developers have one word come up is like they have a container, meaning everything inside the containers don't need to deal anything, meaning the infrastructure and the code related stuff in the same file. You have just
Mhm.
to run a Docker run and everything spun up. So it's work on every machine. Now the developer is actually listening to us, and they actually want how the flow work is actually they write application, and then they compile to the compilation process happening, and then
Mhm.
they some languages or servers give them a proxy server. They can listen on the application and then run on the browser. Eventually everybody is testing their application on the browser. And now if they're reading WebAssembly on daily basis today, I think what they have find is I think what the developer is actually find out right now is like they can run code, and then the compilation happen, and that is eventually run into they compile the code, converting into JavaScript, and now they run in the browser. So meaning there is a more stuff is out of the developer's hand. Like more of the work is now off from the developer. It's just a binary compilation, meaning like you don't deal like I written a code that is on Rust language, and now I don't able to understand how this I can test it on the browser because I need to install uh, Rust related stuff into my system, and then I eventually start up to it. So like I think right now, if the developer are listening to us, what is the current, like I think the most important question for the developer right now, we are actually equipped with the containerization workflow. I created a
Mhm.
container image, then I push into the Docker Hub. The next developer pull the image from Docker Hub, run it into local machine, and then this flow works all hand in hand. But if we transfer everything into the WebAssembly, what is the containerization workflow? Is there
Yep.
a new learning curve for us, or is there this correlated stuff being added?
Uh, so I think the quickest way to say it is there's always something a little new to learn, but in the WebAssembly case, it's much smaller than you might originally think. So WebAssembly kind of draws on the heritage that you saw with Java and with .NET in the sense that you take code and you compile it to a binary format that's fairly neutral. And then you can take that binary format and you can run it on Windows with an ARM processor, or Linux with an Intel processor, or the latest Mac OS with the latest M2 processor or M3, whatever we're up to now. And the same exact binary will run on any of these. So there's that piece, right? So when it comes to the starting your developer journey, it's really a matter of picking the language you want that compiles to WebAssembly and then working in that language for the most part the way you would normally work in a language. So languages like Rust and C and Go and languages that are compiled statically, you just work with the regular compiler and have it compile to WebAssembly instead of to a native format. For scripting languages, there are tools around to help you take your script and then package it up as a WebAssembly binary, JavaScript, Python languages like that, because they need the interpreter as well. And then you've got languages like .NET that are hybrid languages, and the .NET team is building an entire environment that just automatically packages up your .NET application as WebAssembly. So you're seeing different, depending on the type of language, you're seeing different kinds of tooling, but it's all very close to the developer. So it's all really learning and understanding the tools you already have. Then there's this kind of second part, which is assembling that into an application, packaging it up, storing it somewhere. And originally, well, first of all, at Fermyon, we built an application specifically for that. The open source tool called Spin is designed to help you create these kinds of applications. And it's very similar in kind to, say, Docker, where the idea is just to be an assistive technology where you're really doing all the things you normally do in the ways you normally do it, and then it just helps you build the binary and then package the binary up. Originally, we had envisioned, as you suggested, kind of like a parallel set of tools to what the container landscape had. But over time, we started to discover that we didn't really need to rebuild a lot of those things. So for example, you can package up a WebAssembly application into an OCI image. An OCI image is the format that Docker containers are stored in. So what's getting stored is different. It's not a Docker container. It's a WebAssembly application with a bunch of WebAssembly binaries and files and things like that stored in there. But it can be packaged in the same format, which means it can be pushed up into Docker Hub or GitHub container registry or any of these registries that you already use, ACR, whatever the registries are you already use. So we end up being able to reuse pieces of that, which meant as Kubernetes integration and Docker desktop integration started happening, all of those tools could just keep using the same protocols and same libraries they were using already and work with WebAssembly binaries instead of Docker containers. And then it just became an issue of inserting the WebAssembly runtime into the right places so that they could be executed. So I think that's sort of a roundabout way to answering the question very directly, which is this. I think that there will be a couple of new tools you need in order to do the WebAssembly specific bits. But largely, I think we're going to take advantage of the stuff that's already out there. So Fermyon Cloud runs on HashiCorp Nomad and Consul and Vault, but we can also run WebAssembly applications inside of Kubernetes, and we can go on and talk about all of these kinds of things as we go as well. But the reason why we can do this is because we're just taking the tools that we had built already and using them to work with WebAssembly. So the exciting thing is, other than a few little tools here and there, largely the developer experience should stay very familiar.
Yes, absolutely. I think if developers are listening to us, and I'm being in the development of the 4 or 5 year, I know how much of the pain previously had. So this means there's nothing new in there. Basically, what you happening here is like sometime you need language specific thing, and then you can containerize it, pushing it to the repository, and then people pulling out of it. But in order to start development, you need a compiler like stuff in between your the code into the format. With the WebAssembly, you need actually OCI images, like open container initiatives, meaning you have the same image spec and the runtime spec. So meaning more stuff is actually reduces. But the developer is actually using the WebAssembly that is doing the same stuff that already been doing, is container making the container image, building that image, pushing it to the Docker Hub, pulling it, and then it's actually living on these places. So I think that's ideally Heaven plus plus for developer. The number one Heaven for the developer is actually container, and Heaven plus plus mean that the WASM is actually offloading more of the work from the developer, because it's a real challenge. Because when container initially came up, people think like, oh, it's solved every problem we have, but they still needed language specific things in their machine, and then start developing and then start doing containerization on their machine specific things. And now you actually put stuff browser into it. I think there's an ECMAScript, or there is a WASI. Now another question on the same line for developers, we usually see a container runtime interface that is actually eventually running your code. It's container runtime interface. So usually, like currently, what developers needed the container runtime interfaces to run their application by using containerization technology. But if they're using the WASM, so how this WASM fits in? Do you have an intermediate layer that is actually compiling your code into the Java specific thing in the browser, or how is actually? And another question on top of it, like now number one is we need to understand the WASM and the WASM interface. WASI, I think, how do we pronounce it? WASI. And number two thing is like, if the flow is how to describe it, this means it's not just for the browser, but it's outside the browser It enriches more power, portability, enhanced security, agility, and more developer experience outside the browser as well.
Yep.
So I think the most obvious question is here, like WASM, how is different with the WASI, and how the CRI, container runtime interfaces, people are familiar with. Do we expect to see
Yep.
the similar interfaces in the WASM, and why it's being so? Why do we need them?
Yep. Yep. Okay, so I'll start with WASM and WASI and work my way back to that to answer the question. So WebAssembly, the kind of core of WebAssembly when it was defined, was really just the definition of a binary format and how to run it. So it's a very dry specification if you read it. Interesting if you're a compiler expert or a runtime expert. Very dry for the rest of us. But the original design of it was you could take these binaries and you could run them inside of the web browser, and JavaScript could call into functions inside of the WebAssembly binary and be able to execute things. But for use cases like ours, we didn't want to run it in the browser, right? We wanted to run it in the cloud. So we needed a system interface, something that allowed us to do the things with WebAssembly that we normally do with programs, like read standard in and write to standard out, read files and write files, load environment variables, access the system clock, all these very basic things. So that's where the WebAssembly system interface, WASI, came from. It was just a definition of a number of APIs that a WebAssembly runtime could provide to allow the binary to access resources that, at least from inside of the binary, looked like a file system, environment variables, standard in, standard out, things like that. A very core piece of the WASI specification is that all of this has to be done with a lot of security in mind, so that the person on the outside of the runtime can say, okay, it can't do this, it can do this, it can't do this, and control the security very carefully. So WASI has been this ongoing specification. We're at what's called Preview 2. There are 3 previews, Preview 1, Preview 2, Preview 3. Preview 2 is about to land, and Preview 2 provides a whole bunch of system libraries. And WebAssembly runtimes that support these WASI versions can then access various system resources or access things that look like system resources, depending on how the security is set up. That actually is the way virtual machines and containers work. So with containers, the binaries running inside of a container are asking for permissions to execute things. And in this case, they're talking to the kernel. Right. And the kernel is saying, yeah, you can do this. No, you can't do that. But it's a very similar kind of security model. Virtual machines, kind of same thing, except you're emulating the entire environment. So WebAssembly's WASI environment very much sort of is what makes it possible to run WebAssembly like a cloud service. So once you've got something like WASI, then you can start writing code that would execute in an environment like that. But you need the environment to run it. And you mentioned the container runtime interface, right? So how do I actually execute this thing? Set it up so that it's got its file system and it's got its environment variables and execute it. Containers provided a nice, easy way to do this, right? If you're running Docker, you can supply the environment variables and the files on the CLI. WebAssembly really kind of went that same route, where the WebAssembly runtime would allow you to specify the environment. WASM time is the WebAssembly runtime I'm thinking of in this case. You could specify the environment variables, specify what files it could load, and it felt very similar to Docker. But when you're running it in production, you don't really want to run the command line program. You want to run it the way that we run containers. And so we needed something that sat down at the low level and could execute a WebAssembly binary the same way that Moby executes a container or whatever runtime you're using, right? This is where Microsoft came in. Microsoft saw what Fermyon was doing, and we know, we many of us worked at Microsoft, so we have a lot of friends there, a lot of people that we have a lot in common with, philosophically speaking, right? We wanted to build the same kinds of systems, and Microsoft came along and said, we think we can build the piece that runs WebAssembly inside of Containerd, and consequently would make it easy to run it inside of Kubernetes. Docker, incidentally, also started looking into doing the same thing. And so they're both building the same kind of low-level runtime. And Microsoft said, we should just release this as open source inside of the Containerd project. So they've released a project called RunWASI, RUNWASI. And that was a thing that lived in Containerd that took an inbound request to run a WebAssembly module and executed a WebAssembly module using WASI. Once you've got that and the container D layer knows about it, then the container D layer can start telling the difference between a container, and it starts up the container runtime, and a WebAssembly module, and it starts up the WebAssembly runtime. So once you have that whole thing, then, as Docker did, they could introduce spin applications, WebAssembly applications into Docker desktop. Kubernetes could suddenly start running WebAssembly applications. And basically anything that used the container ecosystem and the container D ecosystem could suddenly start executing WebAssembly alongside of containers. So it's a very cool thing because you've essentially got a different in-kind runtime, right? It works very differently internally than the container runtime. But because the assumptions about how to execute something line up pretty closely, it was possible to just create different runners that would take WebAssembly and run it in a WebAssembly runtime, container and run it in container runtime, and just put them all into the same layer, plumb them very deeply into the container D layer so that systems like Kubernetes could just take advantage of it without needing to be rewritten to be aware of how WebAssembly worked.
Absolutely, absolutely. That's make perfect sense for me actually. So now there's, I think, the one question that currently is actually reflected in my mind is like, right now, if you run containers, number one, I think that there's an issue of security in the container, because if you spun up Docker container, Docker is actually giving you the root privileges of the container ecosystem, meaning that your container is actually root, meaning you can actually hook into the kernel, and then you hack the kernel, and that meaning all the workload that is running inside the Docker is going to be compromised, and there is nifty things happening. And then people start doing this kind of remove Docker from the Kubernetes and eventually shift into the container D. And then there's a podman come up, and there's a rancher desktop and a Docker desktop and the podman desktop. That's how the things actually evolve. But do you think, like, now, if we can expect in near future, what happen is people can use to build the images the way they can do it. Number one, if they use WASM, how is the size of the container actually eventually going smaller than expected?
Mm-hmm.
I'd see some of the demos on the internet. There's a KBs of image sizes, not in the MBs. I think there's one wonderful friend of mine who's wrote a book on the Kubernetes and Docker, Nigel Paulson. He did a demo on the internet, and if you look at his container, there's a 4 KBs in size. Number one, how this actually is shrinking the image sizes, and number two, like, is it possible to, instead of using the container runtime interface for some reason, and swap out and use inside the image the WASM interfaces to run the application?
Yep. So again, it's easiest to start with virtual machines and then go to containers and then go to WebAssembly. So virtual machines, the image sizes are just absolutely huge. Gigs and gigs and gigs, tens of gigs, hundreds of gigs. And the reason why is because you start with the kernel and all the drivers, and then the entire operating system, and then all the system libraries and your applications. And then at the very top is the thing that you're going to run, right? So you have these really, really big image sizes. And then again, with containers, they said, okay, a lot of that stuff is just redundant. We don't need to have that in every single image. What if, instead of shipping the kernel every time, we just shared the same kernel? So they cut out a whole bunch of it. What if, instead of having the entire file system, we just package up the file system that we need, and they cut out a whole bunch more? We just install the libraries that our application needs, and they cut out a little bit more. And then they get down from, tens or hundreds of gigs down to gigs and maybe megs. And I think Alpine still hovers somewhere around 25 meg, but you still need sort of a substantial chunk of the operating system to run there. So with WebAssembly, what we decided, kind of the direction that the WebAssembly ecosystem took was, what if we just need the binary, right? What if we don't need the rest of the libraries or anything like that? And what if, maybe you need some additional files, but binary and some files. And then you just strip out all the rest of that stuff. So there's no base Linux image at all. There's no base file system at all. There's no shell. There's none of that. It's just the executable that you need to run. And then we simulate anything that executable needs using WASI again. And so instead of packaging a big chunk of, or a slice of the operating system, we're really only packing the binary we need plus the files that are essential to it. So suddenly we've gone from gigs and gigs to megs, maybe gigs, to kilobytes down to megs, maybe, right? Just it's the size of your application plus or minus some additional configuration files. So that has made it so that, and I love Nigel's, I know exactly which demo you're talking about when you talk about Nigel's demo of this, right? He builds a container image and it's huge. He builds the same application as a WebAssembly file and it's really small. And the reason why is because it's just the executable, just the thing that's needed to execute. And the environment that WebAssembly runs the executable in simulates all the rest of the stuff as the application would need it. So we get smaller. That, of course, does come with some constraints, right? We typically wouldn't try and build something or package something like, say, Postgres, a long-running database that uses the file system extensively and needs a lot of low-level I/O in order to optimize. Those things tend to work really well in containers and tend not to work terribly well in WebAssembly because they're all getting mediated through the WebAssembly runtime, which is going to slow it down. But for microservices, for web application backends, for AI inferencing, for things like that, WebAssembly ends up being a really good language or really good format to be able to package up and then execute those kinds of applications. Let's see, that got to your second question, which is sort of like what does the security model look like for WebAssembly compared to these other ones, right? And again, we can go back to virtual machines and say, virtual machines are based on this idea of the hypervisor. The hypervisor simulates a hardware environment, and the entire operating system runs on top of the simulated hardware environment. Containers said, okay, we don't need the simulated hardware environment. We'll just share the kernel. So you got two containers and one kernel, and this container takes its turn and uses the kernel. This container takes its turn and uses the kernel. And as you pointed out, there's always the potential that if there's a kernel bug, a kernel security bug, then suddenly, you have a good attack vector where one container can kind of attack the kernel and maybe attack other containers or attack the host operating system or whatever. So there's always kind of a danger there. So the WebAssembly model falls security-wise somewhere between the simulating hardware model and the shared kernel model, in that you have a runtime that effectively every single system call that your code makes goes to the WebAssembly runtime, not to the actual system. And the WebAssembly runtime then has an opportunity to say, okay, what am I going to do with this? The user asks to open Etsy password. What do I do? Well, I'm not going to give them access to the Etsy password on the file system. I might have a simulated file system over here that I can give them access to. Maybe it'll have a file there called Etsy password, maybe not, but it's all simulated, right? And so it can do things like that. Or it can do things like, it's asking to make an outbound networking connection. What does my security profile say? Well, it says they're allowed to do that if they go to google.com, but they're not allowed to do that if they go to example.com. And so it can, in this WebAssembly runtime that sits between your binary file and the underlying operating system, it is allowed to make a lot of calls about what you can do security-wise. Now, clearly we're not as dependent on the kernel level security in that case, but we are dependent on the WebAssembly layer security in that case, just like you're dependent on a hypervisor with a virtual machine. And it's a new technology. So all the early security audits have either turned up bugs that have been fixed or said, yeah, it's pretty secure. But we still have to wait. As with any technology, the one thing every security specialist will tell you is, security is an ongoing process, and we all think it's secure, and we learn a little bit and fix a little bit, and then it's a little more secure, and we learn a little more and fix a little more. But WebAssembly does seem to be, stronger security posture-wise than Docker containers, but not yet to have reached the kind of battle-tested, decades-old security posture of like a virtual machine.
Yes, absolutely. That's make perfect sense. I think that just a final question. Because security is a huge domain. I don't want to be in there unless we're talking about whole day about how the things work. But I think there's a few things that the developer is actually doing currently right now. Like number one, they're actually spending time or for the multi-stage builds or multi-architecture images for the different machine. Number one, like if the WASM they have to adopt it, don't think to worry about these build kit or build X that Docker provided. That's number one question. And then number two is kind of similar to that you actually answer. Right now, what the people are doing is actually using open source tooling like Wolfie or OS or making the images sizes more shrinker, just to
Hmm.
drill down to, or sometimes actually people building the images from scratch, meaning everything the image actually built in. So this requires a lot of human effort, and then you
Hmm.
testing and upgrading and patching those images. So basically the two questions that developer actually, I think, really interesting to hear about. Number one, how these actually lift up their job of build X or build kit tool that the Docker provided for the multi system images to work with. And number two, like if the WASM adopted, you don't need to worry about like how they actually shrink the image sizes, what's get the image on the Docker file, and whenever like new dependencies roll up on the base images that we are
Hmm.
using inside the Docker images, we don't need to worry about all these things, or these are staying the same but give us the more benefit of the WASM, or might be reducing the cognitive load from these
Yeah.
stages.
Yeah. This will be a fun one at the end because we can talk about some of the really interesting WebAssembly technologies that are coming out that can hit performance that we haven't been able to see previously in the cloud. But we can start with the earlier question and say, one of the cool things about WebAssembly. So again, it's good to remember that WebAssembly was originally built for a web browser and that we've basically picked it up and put it in a different environment. But one of the things that the web has done extraordinarily well, that web developers have been just conditioned to do for over a decade now, is to build code that runs on any operating system and on any architecture. Right now, it was easier in the web because JavaScript only exposed APIs that could be used across all of these things. But when WebAssembly came along, they had to actually solve this problem freshly and say, okay, we can't have a binary that is built that requires that you run on Intel architecture, because then it won't work on any website that has an ARM architecture, and so on, right? Windows, Linux, same kind of thing. So the specification is built to be cross-platform, where you build it. It doesn't matter if you're developing on Windows. If you compile it to WebAssembly, it'll run on Mac OS and it'll run on Linux. Likewise, if you build it on ARM architecture, it'll still run on Intel architecture, right? So you build it once and it should be able to effectively run anywhere. This is the early promise of Java. And if you talk to the developers who created the WebAssembly specification, every one of them, I am sure, will tell you, oh yeah, we looked at how Java worked. We looked at how .NET worked. We looked at how scripting languages worked. And we learned how to build something that's cross-platform from those ecosystems and from those technologies. So that, I think, is what makes WebAssembly very versatile, where, one of the things that was always frustrating to me was if I wanted to build a container, even if I was building in Linux and I needed to target both an ARM and an Intel architecture, I was still changing my code and building separate versions of the image to run on each of those. I don't have to do that in the WebAssembly ecosystem. That's nice. But this gets us to the next part of your question, which is, there's always room to try and squeeze down on size and improve performance. What does that look like in WebAssembly right now? Because there's not a lot of, unlike the container ecosystem, there's not a lot of cases where we have to trim out extraneous dependencies and things like that. But anytime we're dealing with code, there's always room to kind of squeeze a little more efficiency out of it. And the WebAssembly instruction format is standard, which means you can write tools that we're not involved in writing the code, but can look at the generated bytecode, the intermediate format, and start optimizing it. So you see projects like Binarian, which created a tool called WASM opt, WASM-OPT, and you can run that on a file, and it'll go through and it'll basically do like what a high performance compiler does and say, oh, well, we can optimize this, we can rewrite this, we can throw away this. I was playing around with a Swift file. So I wrote a Swift program. I compiled it to WebAssembly. It was about 90 meg. So it's a very large program. Swift has a very large set of standard libraries, so I assumed it would be a big program. Then I ran WASM-opt on it. So WASM-opt did all these optimization passes saying, can I trim this? Can I optimize this? Can I unroll this? Can I, refactor this? And it produced a 9 meg file. So it downsized the file from 90 meg, 81 meg down to just 9 meg. And that was just optimization passes. So that, you can do some kind of cool stuff like that in the WebAssembly ecosystem that further optimizes. But my favorite project for optimizing is this tool called Wizer, W-I-Z-E-R. So Wizer allows you to optimize WebAssembly beyond what you can normally optimize a standard binary, like a standard operating system binary. And it does it by doing this. It says, all right, the first thing that happens when a program runs is it runs this initialization step. Then when it's done with the initialization, then it starts executing. A lot of times the initialization step is the same. When you're running Python or JavaScript, the initialization step is setting up the runtime, the interpreter, and loading all the script files in. .NET, it's setting up the interpreter and loading all the object files in. In Java, it's loading all the class files in. The same thing happens every single time you start the program. Well, what if you, using Wizer, run the initialization step, load all of this stuff, and then refreeze that as a separate WebAssembly binary. And then you can start up faster than the native environment. So we do this now at Fermyon, we do this with both Python and JavaScript. In Python, we kind of pre-init, load all the Python files in and initialize them, and then freeze them back out as a new WebAssembly binary so that it can start even faster than just running Python space, foo.py. And that's just a really cool way that WebAssembly as a technology that is sort of like a binary format that you can inspect. Because it has that as an attribute, it means that we can start building tools that really start to optimize for performance. Now, again, this might not matter in a case where you're running a long-term server process. And that's the kind of thing that containers are excellent for. If you're running a database, you want to run it in a container, and it's going to start up and it's going to run for days or months or weeks or so on, right? But if you're talking about a serverless app where you need to start up really fast, handle something and shut down really fast, these little performance improvements that you get with Wizer and with WASM that'll cut down the load time and cut down the startup time, they can make a really big difference in the overall quality of the overall performance of the applications that you're using.
Yes, absolutely. I think that the most encouraging bit is here, because I think there's currently, I know a lot of the developer is still using Docker for the multi-architecture images. Every time to write in Docker file, you have to take care of this. This image has to build on Mac, on Edge devices, on ARM 66. This is look nerdier people for nerdy people. This is look inspiring. But to be honest, it's a lot of work. If WebAssembly can offload this, it's a huge shift. This is not a very small problem they're solving. This is a huge problem. This is a universal problem. So Docker actually solved the universal problem of virtual machine. And actually, WASM solved the universal problem of Docker. Like, if you have to build the images in a different architecture, that's really interesting. And then you mentioned, on the security side of things, look at the container ecosystem is full of security, supply chain security. You have scanners, you have Trivi scanner, then you run GitHub Action that runs the images and that check the vulnerabilities inside. If WASM do these kind of heavy lifting, this is a huge. I think there's no point of people were learning and adopting WASM as well. But during this discussion, I think the end of this discussion on this note should be container is actually revolutionizes the ecosystem, the huge ecosystem. Look at the container. What it does is for the developer, they actually is they start with the Helm, and now they actually there is so much for the developer to consume about it. Number one is actually they started Kubernetes. Then the service mesh wave coming up. Then there's a policy and governance. Then there's a monitoring and observability. Then there's a chaos engineering. So now people thinking do WASM extended the existing landscape? If which of the pieces the WASM extended? The next question, if they are not extended, what are the existing ecosystem of tool that the WASM uses? That's the question number two. And then the similar question on the top, if WASM created a landscape, what the landscape should look like?
Yep. I think there are two ways to look at it. The first one is you can look at WebAssembly as a fairly generic tool for building things and view it as a thing that can be plugged into different environments, right? There's no reason you couldn't take a WebAssembly runtime. In fact, many people have done this, including Amazon Prime and Disney Plus and BBC. You can take a WebAssembly runtime and you can embed it in a streaming platform or a TV or something like that and use it there. WebAssembly and plug it into some existing environments. I tend to like the view that you take more and say, okay, so we've already built this big cloud native ecosystem. Can WebAssembly just fit into it? And if so, what are the pieces it uses? And I think the answer is, yeah, essentially we can just put it right into the existing landscape that we already have. And so it is easy to run inside of Kubernetes. Well, what does that mean? Well, it means, first of all, we can execute them in Kubernetes. Second of all, we can take advantage of the service meshes and the monitoring and the entire SIG store and the entire software supply chain toolkit. We can use all of those with WebAssembly. So we're really just adding one more tool into an existing stack. And this tool happens to solve what I think is a fairly fundamental cloud computing problem, right? How do you get instant startup times? How do you run these things very quickly and then exit very quickly? How do you be really efficient with memory and CPU? That's a low-level set of problems to deal with, but you can still plug it into this higher level architecture like Kubernetes, or for that matter, like Nomad's ecosystem with Nomad Console and Vault, or any of these other ecosystems. I think that's the more promising route. And what I would like to see over time is for us to just continue to use any tools that serve a purpose and continue to make WebAssembly, interact with those the way it should. It's turned out so far to be fairly easy to just reuse these things. So, for example, we can take SigStore and Cosign, right? Tools used in software supply chain. Turns out, spin applications work just fine. You can cosign your application, you can verify it with SigStore. All of it just works fine. There were no changes at all necessary for that. That's really exciting, right? Others like Containerd, we talked earlier about how it required writing run WASI, a shim that would run in Containerd. And there will likely be parts that are just not as important. When it comes to being able to monitor the security profile of a WebAssembly binary, you don't need a container scanner. Instead, you can inspect the WebAssembly binary directly. So there will be some new security tools that evolve specifically around WebAssembly, but I think they'll just kind of slide right into the existing stuff we've built for cloud native. So to me, WebAssembly's most promising path forward is really through the cloud native ecosystem. And I think to the greatest extent possible, we want to reuse those tools and allow developers to build things the way that they have been. Platform engineers are the important ones here, right? We want to make sure that the platform engineers understand how WebAssembly fits into their existing platform and can just keep running it without having to relearn everything. And I think that's a big goal of the current cloud native WebAssembly ecosystem. That's the kind of stuff that we end up talking about at WASM Day, the day before KubeCon starts in Chicago. So if that's the kind of thing where you're listening and going, oh, I really want to hear about that, watch the WASM Day presentations from the last KubeCon in Amsterdam, and or come to WebAssembly WASM Day in Chicago, and you'll get to hear these kinds of conversations happening real time.
Yes, absolutely, absolutely. I think there's final two questions left. I will keep on debating because I think this is the most interesting topic of both of us, but we'll have to wrap up. But I think there's a one final trickier question, I think might be. Let's say if people are not adopting, the startup, the companies not adopting WASM going forward, what are the things they have to miss? And what are the big consequences of this of not adopting WASM?
That is a fantastic question, because it really gets to the heart of what makes a technology good, right? If you say, what's the cost of not using the technology, suddenly it bubbles up. Oh, I see, I understand. And one of them is just performance, right? That's one of the things we really set out to tackle, was performance. But performance is actually hiding a bigger issue. And I think particularly as the world, as the world economy sort of contracts a little bit, you start to see the real issue here, which is we have built the cloud on the idea that we run things all the time and we pay by the minute, and it's getting more and more expensive for us to run things in the cloud. A huge part of our motivation for building a new kind of cloud runtime was to say, well, how do I start to cut the cost down, right? I can do less, but I don't want to do less. I want to do more and still pay less, right? So how do I do more and pay less? And WebAssembly, and again, this is really the way serverless in general works, but WebAssembly particularly is so well suited for this. When I can not be running a server all the time, right? When the piece of software is only running when it's handling a request, it means that I can start cutting down on the amount of compute resources that I use. So let's compare this to Kubernetes, right? On paper, the limit for Kubernetes is you can run 110 nodes per 110 pods per node. So even in Amazon, this takes like a 24 XL or something like that before you can run this many pods on a node. WebAssembly can run about 1,600 applications per node, and you really only need about a 2XL sized image to be able to hit that. The reason why is because these applications are only running when they're handling requests. So starts up, handles a request, shuts down, and everything like that. So you're sharing the CPU more effectively. You're sharing your memory more effectively. If you're doing AI, you're sharing your GPUs more effectively, right? And once you can share more effectively, you can start lowering costs while still accomplishing the same or more things. So that, I think, is where, if you were to, well, you did ask me, to me, the thing the most valuable about WebAssembly, the thing that I would miss the most about this is this idea that I can get a lot more done with the same amount of compute power, or lower the amount of compute power and consequently lower my software bill, my cloud bill. And I think that's really, really important as cloud matures, because we can't just keep making more and more services that are increasingly expensive. We'll all be broke before we can build the applications we want to. So WebAssembly is one of those efforts to really start pushing the cost of cloud down.
Yes, absolutely. That's super important. I think you phrase it wonderfully well, because if you look at the container and Kubernetes ecosystem, what it does is it solves a generic problem and it's create a generic problem. What have ended up happening here is plethora of tools solving the same problem with their own initiative or different ways of solving, but it's end up happening. Developer have to learn a lot of tooling, and when the startup is actually eventually solving the business need, their brain gets crackier. What should I choose, and how do I convince my developer why should I choose it? It's not just why I choose it, why I choose it over other different tools available. So the conversation, it actually tells me the WebAssembly is for solving a generic problem with generic set of tooling that exist in the ecosystem, with the mind that it is actually eventually saving the cognitive load from the development team, and plus the cost of the cloud. That's huge. This is not a very easy way to think about it. Cloud cost is a huge challenge currently. So I think that's a super important. Another, I think, another question, and we wrap up on this thing. Like, if in a few sentence, in the few words, where do you think the next 6-7 months, down to the closing on the year, the things are happening in the WASM world?
So the next big set of things happening in WebAssembly are all in the standards bodies, and they have really boring names like WASI and the component model, but they're really, really exciting technologies. And so I'll talk just about the component model here. So if you can compile everything to the same binary format, then it should be possible to make things talk back and forth across that binary format, right? So you can think of this as sort of like the way gRPC works, right? Once I've got a common protocol and a common way of describing things, I should be able to share information back and forth between two gRPCs, microservices. What if we can build an environment where, instead of having microservices that are connected by a network and have to send everything over JSON across them, we can actually run them side by side in the same runtime and be able to directly interact with them through the runtime without having any network or anything like that. All of that sounds very vague and lofty until you rephrase it this way. Imagine if I can import a library written in Python into my Rust code, and then import my Rust library into C code, and my C library from Go, and my Go code from Ruby. Suddenly, it doesn't matter what the origin language is of any of these libraries or pieces of code, because they all get compiled to the same binary format. So what really excites me, and where I think by the end of this year, we'll see WebAssembly sort of really show off a brand new feature that we have never been able to do before, is this idea of being able to share libraries that have been written in different programming languages without the developer even having to know what the programming language it was written in. So if you think about, let's take YAML processor, for example, a YAML parser, right? JavaScript's got several YAML parsers. Swift's got some. Rust got some. Every single language has implemented a YAML parser. And so we've got thousands of YAML parsers. Why do we have that many YAML parsers? If we can compile a YAML parser to a binary format that any language can use, then suddenly we don't have to keep wasting our time writing the same thing in every single language. That's where I think WebAssembly will really start to show promise, because it makes developers a lot more productive because we don't have to reinvent the wheel. And it makes developers a lot more productive because we don't have to deal with discrepancies between the JavaScript version of this thing and the Python version of this thing and the Go version of this thing. They're all just sharing the same libraries. So to me, I think by November, December of this year, we'll start to see this kind of pattern emerge. That will be a really big moment for WebAssembly and really start to level it up to do something that we haven't been able to do before.
Yes, absolutely. And that is actually hard. You actually phrase this perfectly. If everybody listening to this is a huge heaven plus plus or secure of the heaven, because this is a huge problem. You actually phrase it perfectly. This is not the problem of the developers. This is the problem of the open source communities and the language creators and the library creators. It's a huge problem. Like, you create a library and then create a parser for every different languages. And that is parses like Yammer. There's so many for JavaScript, for Ruby. There's so many parsers available. And if this happens, then there's a lot of momentum. I think I think then you have to be careful of rating people's tweets of thankful for this effort, because that is huge pain solver.
Yeah.
That's a huge pain solver. I think that's required of whole. And I think that I'm really happening. I think this should be happening because WebAssembly is actually has capable of doing this thing.
Mm-hmm.
I think people are already working on it. And I think if somebody listening to us, and if you are doing these kind of things, Matt is a great person to communicate with these kind of stuff, and wonderful person. He created Helm project. Now the next WASM thing is getting traction. Matt, why oh why? It's a great story to work with you. So I will wrap up the episode, and let me correct me if I wrong with concluding any of the things here. So containers offer a consistent and isolated runtime environment, allowing for easy development and deployment and scaling of application. They provide portability and encapsulation, making it simpler to package and distribute software across different environments. On the other hand, WebAssembly brings near native performance and cross-platform compatibility to web application. It enables running code written in various languages within the browser, opening up new possibilities for building powerful and interactive web experience. By combining container and WebAssembly, developer can leverage the strength of both technologies. Container provide a secure and flexible infrastructure for deploying technologies, while WebAssembly enhances the performance and versatility of containerized application. Thank you very much, Matt. And thank you very much for everyone tuning into this channel and listening to this episode. We will meet again soon with another expert guest right here on Cloud Native Podcast. Don't forget to share and subscribe and comment below what topic you want us to cover next. I will be continuously reading. Talk soon. Stay safe, stay healthy. Have a wonderful day, everyone. Bye bye.